Good morning. It's 9 a.m. here in San Diego, so we will begin the webinar. Thank you very much for joining us. So today's webinar is on covalent ligand docking and screening. During the webinar, please use the question panel to ask questions, or you can raise your hand at the end and I can open your mic. My name is Andrew Ori, and if you have any questions after the webinar, please feel free to email or call. Anybody who's registered for this webinar, you can download ICM, and we will send you a 30-day license so you can follow what is going on in the webinar. You just need to download the package and then send me the 12-character host ID that's reported when you open the software. This is the fourth webinar in the series, so you can watch older webinars on our YouTube channel. If you just search for MoleSoft on YouTube, you will find the webinar archive. Just a quick slide about MoleSoft. We are based in ICM, in California, and in San Diego, California. The company was founded by Ruben Abagayan, who's a PI at UCSD. Max Totroff is our principal scientist, and Eugene Rausch is our principal developer. If you're wondering what ICM stands for, it stands for Internal Coordinate Mechanics, which is the way we define our atoms in ICM using torsion angles. And you can read more about ICM using in these original papers in 1994. And you can also read some papers in 2017-2018 which describes the performance of ICM in the blind D3R docking, screening and affinity prediction competition held last year, where ICM performed very well. So in today's webinar, we will be looking at how to set up covalent docking in ICM Pro, how to sketch and apply a covalent docking reaction mechanism, then how to run covalent docking, and then how to screen a database of chemicals to that to a pocket. And then also, if you have a covalent bound inhibitor that you want to try and optimize, you can do that inside the ICM 3D Ligand Editor. So just a quick slide on covalent ligands. So there's been generally a reluctance from pharmaceutical companies to consider covalent inhibitors, primarily because of concerns of high toxicity, but there are obviously some famous drugs that are covalent inhibitors, such as aspirin, penicillin, omeprazole, proton pump inhibitor, and Plavix, the anticoagulation drug. So there's more than 50 FDA-approved covalent drugs on the market. So this was a useful review article if you're interested in reading more. So some advantages of the targeted inhibitor, which I guess is the reason why you're at the webinar, because you know there are some advantages. The first one is probably, the main one is it can lead to very, covalent binding can lead to very high potencies, and sometimes exceptionally and good ligand efficiencies as well. And so the covalent bonding allows high potency to be routinely achieved in compounds, sometimes with low molecular mass, which is sometimes beneficial. Another advantage is selectivity. So if you have a family of proteins and you want to develop a selective inhibitor, you may identify a nucleophile that is rare across the family, and then you can target that. That selective residue, and like a cysteine or a serine residue perhaps. And there's also some advantages in terms of pharmacodynamics. So the restoration of pharmacological activity after the covalent irreversible inhibitor is bound requires sometimes resynthesis of the protein target. So this has a potential and advantage in terms of drug pharmacodynamics, and in terms of dosing and the duration of the pharmacological effect. And obviously these covalent inhibitors can also be used as biomarkers. So inside ICM Pro we have all the tools for covalent design and optimization. So you need to have a target where you have a nucleophilic amino acid on the protein and then the electrophilic moiety on the drug molecule. An example of a success story was a collaboration between Molsoft and Max Totroff, our principal scientist, with Rempex Pharmaceuticals, where Molsoft ICM Pro was key to the discovery of this cyclic boronate beta-lactamase inhibitor. And you can read, it's an FDA-approved drug. You can read more about the development in this paper here. Another exciting paper that was published last year on covalent docking showed that ICM Pro actually, this is a completely independent evaluation by Andrea Scarpino, and it showed that docking accuracy for ICM is 90% compared to 65 to 75% for autodoc, CoVdoc and fitted, and 50% for MOE. And this is a figure from that paper. So Molsoft ICM Pro outperformed the other software for reproducing the experimental binding modes for covalent ligands and also for scoring. ICM also performed very well with more challenging ligands with more than 35 heavy atoms. And then in this paper there's quite an interesting side test where they put ICM Pro against Glide from Schrödinger, and ICM performed with very well using non-covalent conventional docking as well. So that's a paper you can read. I can provide that if you're interested in reading more. Another benchmark was developed by London, a group by London et al., and it includes 61 complexes of beta-lactamases and PPBs with boronic acid and beta-lactam inhibitors. And ICM outperformed other methods in terms of RMSD accuracy as well. Okay, so practically how do we do this in ICM? So if you've been attending the earlier webinars, you would know that we, by default, we use grids, to represent the binding pocket. So because we do that, we need to have some special way of handling the covalent bond that forms. So what we use is that we use a reaction. So we sketch the free ligand before binding, and then the product of the covalent binding is sketched here. So here we have the boron. This is our chemical that we're docking. You see a boron with hydroxyl group here, and then we have two R groups. So we have R1 coming off here, and then R2 coming off here, and then the resultant ligand binds. In actual fact, what we do is that we kind of what we call mask the docking grid. So you can see when you display the region of your covalent bond, this is a serine, that it will be masked out. So it has these dotted lines. It's not included in the grids. So the input ligands, you can either sketch them or bring them from a database, and they can be automatically docked based on this reaction or any other reaction that you may have that you might need. So we're going to look at an example of a multi-drug resistant pathogen, and there's the penicillin binding protein that we're actually going to look at, which is a key therapeutic target. It's an essential enzyme responsible for the final steps of peptidoglycan synthesis, and is covalently inactivated by beta-lactam antibiotics. In this example, we have quite an old one called Aztreonam, and the PDB code is 3PBS. So we will go to ICM and we'll go through the steps of how to do this. So you should load ICM by just double clicking on your on an icon usually, and then we've gone through many of these things before. So in the previous webinars, so we're using the PDB search, and we can read in 3 PBS. This brings in the crystal structure. It has a resolution of 2 angstroms. It has an A chain and the inhibitor bound, and also some waters. It'll be interesting to see where the covalent bond is formed. So a quick and easy way of doing that is to go to the inhibitor, right click and choose pocket, and choose ligand pocket interactions, and then just center, select the ligand and then center on that region. And we should find the serine here. So the ligand is in yellow, and the serine 294 is making this covalent bond. Okay, so we now need to set up, so in this example we're going to redock estranam, and then we can also dock some other beta-lactam inhibitors as well. So we're going to, we discussed in the past about water molecules. So some waters may be needed, some may not. In this example they're not required for the ligand to dock correctly, so we're just going to delete them. And one good test is obviously to, if you don't get the exact pose of the crystal structure, then maybe there is a water there that is required for that pose to be achieved. So we're also going to move the inhibitor out of the pocket. So we right click on the inhibitor and choose move from object. Although graphically it looks like it's still in the receptor, it's actually a separate object. So this ligand and this receptor don't see each other. So basically it's an empty cavity for this structure. If we left the ligand in there, we wouldn't get results because they would be the ligand would be included in the maps, and so there would be no cavity to bind to. So the first step is to convert to an ICM object. Right click on the receptor, choose convert PDB. I was going to choose replace the original. If you were doing this properly, you would optimize hydrogens, which takes a couple minutes longer, and I don't have time for that, so I'm just going to uncheck that and just go OK. This will convert the receptor to an ICM object. So now you can see in the terminal window it's told you what it's done. It's optimized some asparaginins and glutamine residues, and we can now see that it now says ICM here, so it's ready for docking. If you go back to a previous webinar where we discussed this in more detail. So where's the binding pocket? We kind of know where that is because we have an inhibitor here, but we could just run ICM ligand, go to Tools, go to 3D Predict and choose ICM Pocket Finder, and this will find the binding pocket as well as other cavities, allosteric sites. So it's found a number of different pockets, and I'm pretty sure the biggest one is going to be the one where this one, number 1, is the binding pocket for this inhibitor. But it's also found some other allosteric sites around the structure. We can ignore those. Okay, so we need to set up the docking project. So we go to docking menu, say new project, and then we need to give the project a name. It has to be 4 or more characters. I'm just going to choose Covalent and then the name of the PDB file. The project folder, this is where all the maps and all the output files and everything will be stored. Then it's asking you what the ICM object is. The receptor object is 3 PBS. It's the ICM command line language, A_3PBS. And the site is the first pocket it found, and we say define site around mesh here. So it says G_3PBS1, which matches this blue pocket. So if we click here, define site, we'll see that we have green crosses all around the binding pocket. So there's an option here called make receptor maps immediately. If we were doing regular docking, we would leave this checked, but because we're doing covalent docking and we're going to have to remake the maps, we're just going to uncheck it and go OK. As before, we have this probe, which you can just leave in the middle of the pocket, and then that purple box, you can play around with the size. We talked about that before in a previous webinar. So now the docking is set up. You can see now we have a new object in our ICM workspace called Covalent_3PBS_rec. So this is the structure that we're going to dock to. So it's also the structure that we need to tell ICM where the covalent bond is going to, which residue is going to be our covalent bond, make the covalent bond with the ligand. So I know that I was going to undisplay the pocket, it's not needed. So we know that in this case the residue is the serine residue. It's serine 294, so you can expand the sequence level here and choose the serine 294. Okay. And you can see green crosses on here, blue on that one residue means that's selected. If we zoom in, we go straight to that residue. Okay. So I'm going to label it just for. Okay. So the next step in the docking project setup is to tell ICM that we want to use this serine as the covalent, as the nucleophile. So we go to docking, we go to covalent, and you can see that we have here modified residues, 1 res. Okay. Before we go any further, I just want to show that inside ICM we have a number of covalent reactions already sketched, already provided. So I want to show those before we move on to the next step. So we go File, to view those reactions that are already provided. You can also see them in that docking covalent window, but it's more convenient to look at the SDF file. So go to File, Open, and you go to your directory where you downloaded ICM, which should be in like Program Files, and then MolSoft, and ICM Pro, and I think the file is called Covalent Mechanisms. So if you open that file, you can see in this table we have more than, make the table a bit bigger. There's more than 32 different reactions pre-sketched, the more common covalent reactions that you can use. So you can sort by, so some are for serine residues, you can sort by residue, and some are designed for cysteine as well. There's also one for threonine and also for RNA. So you can see the name of the kind of chemical that's going to of the free ligand, the residue that's going to attack, and whether it's going to be the protein target, likely protein target for this reaction. So all these are inbuilt into ICM, so you can select them. If the reaction that you need for your free ligand is not available, I will show you how to sketch one in a minute. So with that table, we go to docking and we go to covalent. You can see that we've selected that serine. We have one residue selected, and we can click on this button called Load Preset Reactions, and that loads that table that we have already shown, and it's in this side panel. So we need to select the correct reaction for what we're doing. and I need to find it in this list. Just 1 second. So here it is. It's the beta-lactam serine reaction. So we can select here, and we click on the button called Add to List, and that shifts it over here. Okay. So this is the reaction we're going to use. You can actually use more than one reaction. You just need to select more, and so if you have a database with different chemistry in it, then you can screen on the fly multiple different. It'll be to the same serine or cysteine, but you would do it on the fly, so you could select more and drag them over here. But in this case, we just need this one reaction shown here. And I'll talk more how to sketch this later if you want to do it yourself. So, and then you go OK. And then it says remake receptor map. So it's going to make the receptor maps for us using the serine. You can see the serine is now, maybe not through the GoToMeeting, but it's sort of hashed out, which means that that region is not going to be included directly in the maps. It's going to allow some docking. Okay, so the docking is basically set up now. We're ready to go. So now we need a residue, a ligand to dock to this residue. So we can't dock directly that ligand that we extracted, the aztreonome, because it's already in the product form. We want to dock ligands that are in the free ligand form. So we'd have to go. We need to go to to dock that ligand. We need to sketch it first, or read it in from a SDF file or from Smiles. So to sketch it, we can go to the editor here, this button here, and you could sketch it, or you can use the dictionary that we have inbuilt into ICM. And if you type, it will start populating the dictionary. You'll find the ligand that we're going to dock here. You just single click, and it should load in the window. So you see the beta-lactam ring and the rest of the ligand. If you're interested in the properties of the molecule, you can click here. When you make modifications, those properties will change on the fly. But we're going to place this molecule into a chemical spreadsheet and then dock it. So to place it into a chemical spreadsheet, we have a button here. We just click on that one and give the table a name and go OK. Okay, so now our chemical is here in a chemical spreadsheet, so we can dock it. Alternatively, you could save it as an STF file and dock it. So to dock, we go to Docking, choose Dock Chemical Table, and it asks for the name of the table, and you can just go OK. And then you'll see at the top it says one background job is running. If we go to the terminal, if we go to Windows and choose background jobs, we'll get a bit more information about the progress. You can even view the output as it's running. So when you do it directly from the docking dock window, it's using the default parameters for thoroughness, which is the length of simulation, which is 3, and it will return the 3 best conformations in terms of energy into a stack as well. So provide both of these options. If you wanted to be more, if you wanted to change these options, you would have to go docking, oh, it's finished. It's going to go OK. If you wanted to have different options, then you would uncheck in docking dock table. You would uncheck this option, dock immediately, and then you can increase the thoroughness or number of conformations and other options here. Anyway, it's finished, and so we get a ranked hit list of the docked results. And you can see in the hit list in the SDF file that it's showing that there's a covalent bond here with serine 294. So we do, if you want to load that structure into the receptor object, you would do just a single click in the table, and that loads the ligand into the receptor. And you see it's ranked by score, so this is the one with the highest score. And because we had 3 conformations, we also have 3 other docked conformations that you can toggle on and off, view them here based on score. So we can compare it to the crystal structure one. Bearing in mind I didn't optimize the hydrogens, so it may not be 100% perfect. But the crystal structure one is here. So the crystal structure is going to be green, and the docked is yellow. So it's a pretty decent match between the ligand. So if you also want to dock a chemical spreadsheet, for example, you would go to docking and then choose setup batch from SDF file, and then browse, and I have a larger an SDF file with for which I took some beta-lactam molecules from PubChem, and then you can just dock those, and it will dock them, and you get an option for the effort thoroughness, which is 1 in this case, which is sort of designed for high throughput screening. But if you've got time, you'd maybe use 3, and you can also split the jobs up into multiple cores on your computer, and just go OK. And so that's running that. It's actually screening. I'll show you the database. It's PubChem. So this is just extracted from PubChem going to the search tab, going to PubChem here, and searching for these beta-lactam molecules. Okay, so that's running in the background. So we can leave that running, and maybe we can have a look at the results in a little bit. So in this example, we used the inbuilt reactions that are provided with MolSoft. But in some cases, you may not be in that position. You may need to sketch the free ligand and the product yourself. So to do that, what we do is we go to sketch that reaction. We go to the sketch editor again. This button loads up the 2D ICM molecular editor, and then we would sketch the. I'm going to delete some things. So we need to sketch the region of our free ligand. So let's just compare it to this one. So here we sort of we're sketching the general reaction equation for the acylation of the serine side chain by beta-lactam. So we have we need to just delete some side groups here. We can add this is going to be an R1 group, and then we have the oxygen, and we can then add additional R groups here based on this structure basically. So you can change stereo by right-clicking on the bond, and this is to define as R1. We would have to right-click on the atom, choose element R1. You can make this one R2, etc., etc. And then we need to define the product. So the first thing we need to do is sketch at least 2 carbons of the serine residue that we're going to be docking to. So you'd have the serine, the two of the carbons, and then in this case we have a we can then draw the rest of the free ligand. So we have a double bond to the oxygen here, and then sketch it out how the product, and then we have the nitrogen here, and R1. You have to also have the R groups have to match the number of R groups here. I need to add these in a minute. It's a bit time consuming to do it live. So you sketch the R groups as well. So stereo up, stereo down. This is R2. This is R3. You right click, and then we have R4 and R5, and I'll add this stereo. Now free ligand has to match, so I need to fix this to better. So this would be R2 and R3. So this is R3. So R2. This would be R4 and R5. One will be down, and the other would be up, which we need to also fix in the products. This is R4, and then we sketch R5 here. Actual fact, R5 is, in this example, stereo is up, so it needs to match here as well. Okay, so the reaction is done. You just need to separate the free ligand and the product using this arrow, and you get the arrow from here. Just click. So just as long as these are separated somehow, then ICM will recognize it as a reaction. So we can then, once you've sketched your reaction, you can store it to a table just by clicking to this button again, as we did before, and just give it a name. Actually, one important thing which I didn't show, we need to define the serine residue as well. So this is the serine, so we need to label the serine as it is in the crystal structure. So this would be C alpha, and this would be C beta. So to do that, we right click on the atom and choose edit atom label, and then you can put C alpha, CA, and CB. So edit atom label and choose C beta for carbon beta for the second one. So this defines the serine residue, and then we have the product bound here. So probably the easiest thing to do is to read in that it's called covalent mechanisms, and then you can edit that table and for it. So the serine would already be drawn. You just need to edit your product. So you can read that table in and right click and choose edit reaction, and then you can edit it here. But the one I just sketched I can put to a new table just by clicking here and go OK, and then we should have that where did it go? So yeah, so now it's the reaction that we just drawn is shown here. So then if we go to docking and then we choose covalent again, if you remember we select the serine residue, and then you can just, rather than use the inbuilt reactions, you can choose source reaction library and choose the table name with your reaction that you've sketched. It's a rather convoluted way to do it. And then you just select it and then add to list, and it would add it to this table here, and then you just do the docking as we did earlier. Okay, so the screening of the large database is still running, but we can make an interim hit list for any database we were docking that larger SDF file from PubChem. So to make a hit list, just go docking, make hit list, and then choose OK basically, and it should generate the hit list. So far in that time we've screened 10 chemicals from that SDF file. We can rank the hit list by score by clicking on the column header, and just double clicking will display the molecule, or you can display them using the toggle button here. So that's more virtual screening of covalent inhibitors. So in some cases that you may already have a crystal structure with the covalent inhibitor bound, so you want to maybe optimize that. And so in the first webinar in the series we looked at the 3D Ligand Editor, which was developed with Novartis and medicinal chemists there. So you can edit a ligand in 2D or in 3D and try and optimize for affinity or for specificity your ligand. And so you just make a change here and then commit the change, and you'll see the effect on the binding score. Everything can be undone and redone, so you can just explore different ideas with no concern about ruining your docking setup. And inside there's docking minimization, methods for induced fit docking, and also 3D pharmacophore. But for covalent, we have an example. So the example we have is, let's just get a clean ICM session. The PDB file is 1ms6. So if we load that, and we can observe that there is a covalent bond with this residue, with a cysteine, I think, in this example. So if we just right-click on the ligand that's in the PDB file and go to Pocket, Receptor-Pocket Interactions, click on the ligand again, and we should find the cysteine. Yeah, cysteine 25 is the covalent one. So in this example, we would imagine that we're quite far ahead in our covalent inhibitor design process. So we even have a crystal structure already pre-made. So we may want to look at how to maybe some different substituents at different points to try and improve this ligand in the Ligand Editor. So the first thing we need to do is we'll be using the Ligand Editor tab here rather than the docking menu. The docking menu is more for screening. This is for more one-to-one interactive editing. So we would first click on the Ligand Editor tab, select the TIL-ICM, which is the ligand. In this case, there's only one ligand, one small molecule in this protein structure, so it finds it immediately. And you just go OK. So now the ligand that we're going to optimize is here. Then we need to set up the receptor. So we need TIL-ICM, which of the molecules is the receptor. So we click on the Setup Receptor button, and TIL-ICM, the receptor object is 1ms6. There's options here which we discussed in the past, but we'll say make box, which will be the docking box around the existing ligand that we've told ICM is here. So we just go, we have the purple box, which we briefly saw before, but you can change the size of this by dragging on the corners. This is where the docking will occur. We go OK. So in this example, so by default it shows this this pocket surface, which gives you a better view of where there's space. For example, here there's a hydrophobic region for which you could maybe build out towards, or here. So it's colored by properties. So it's trying to guide you. So it's saying that a modification here, you would maybe want to add a hydrogen bond acceptor in this red region, and same here, maybe a hydrogen bond acceptor would be maybe a good addition here. Blue with hydrogen bond donor, and green is hydrophobic region. So in this example, our inhibitor, we have the cysteine residue. Let me try and make that a little bit bigger. I'll highlight it, this cysteine 25. And we need to modify the nitrile group here in order to obtain a terminal hydrogen to define the connection to the receptor. If the compound is represented in an unbound state, like this one is, then one needs to make the necessary modifications. So in this particular example, we need to change this triple bond to a double bond in order to get a free hydrogen in order to make the correct connection with the cysteine here. So in the Ligand Editor, we have tools for modification. So to convert this triple bond to a double bond, we go to the double bond button here, select, and then select on the bond. Now you can see we have the hydrogen here, which we can now use to tell ICM to make the covalent bond with this nitrile and the cysteine 25. So to do that, we first need to select that hydrogen that we have available and any atom on the cysteine. So we use the atom pick tools here with the green cross and click here, and then go to the advanced button in the Ligand Edit tab and choose define covalent inhibitor. Okay, so now we have the covalent bond made. Now we can make changes to this ligand. We can evaluate the score. We have a score of minus, by clicking here, we have a score of minus 38. We can make modifications in 3D just by simply selecting groups. If you wanted to do a small substituent screen, you can select a number of groups and then choose the position you want to add. And it's doing a small virtual screen of each of those groups and evaluating the score of those. We went through this. If you go back into the YouTube webinar archives, you can view other things you can do in this environment. So for example, we can display the receptor pocket colored by binding property shown here, or you can show that pocket that's initially shown, which is called the ligand pocket surface, which gives a better idea of where there is space. So you can quite clearly see there's no space here, it's cut off. So if we add a big substituent here, then it's going to complain and give a bad score, I think. You can see that these show that there's a clash between the receptor and the ligand. And for the purposes of this webinar, you can see that the covalent bond is always maintained between the ligand and the receptor. So you can also redock the ligand. You can minimize it here using this button, or single click on the docking button, and that will minimize. It will dock your covalent ligand. Okay. So those are the main steps in ICM. I had some questions that I'll try to get to in a bit. Just want to thank you very much for your attention, and thank you for your support of the webinars. The next webinar is next week. It's the final one in the series, and it's on fragment docking and linking